Hello, my name is Antonetta Axup-Vecchio, and I teach middle and high school science for Harmony Public Schools in Waco, Texas. I have been on site at West Point Military Academy here in New York, working with Lieutenant Colonel Will Cook in the Department of Physics and Nuclear Engineering.
Hi, my name is Connie Michael. I teach fifth grade at Crow Agency Public School on the Crow Reservation in Montana.
Hello, my name is Jessica Capece, and I teach fifth grade at Evergreen Elementary School in Pennsylvania. Our group created a 5E STEM unit on an investigation of light from visible to invisible. Our unit on celestial phenomena and light began with engaging students' curiosity about why some sky objects appear brighter than others. On day one, we sparked questions about the sun's impressive brightness and size compared to distant stars. This helped us introduce the idea of apparent brightness versus actual brightness, setting the groundwork for understanding how distance plays a crucial role in how we perceive light from space. Students observed images and videos of the sky, recorded their notices and wonders, and started forming their initial ideas. We then shifted focus to various light phenomena like rainbows and lights through colored filters, prompting students to hypothesize about the source and nature of these colors, always linking them back to the sun as an energy source. This introductory phase was crucial for pre-exposing students to concepts like the visible spectrum and how light interacts with matter, which are foundational for deep dives. We also explored how colors can represent data in images such as heat maps or astronomical images, leading into a color by number novella activity that revealed how scientists use color to understand complex information.
Day 2 and 3 plunged students into hands-on exploration of light's properties and apparent brightness. On day 2, a key activity involved observing M&M candies under different colored lights. This experiment provided a tangible demonstration of color perception, light absorption, and reflection, illustrating that an object's color is determined by the light it reflects. We also showed how prisms, water, or CDs could split white light into a rainbow, demonstrating the visible spectrum. On day 3, we continued with colored cellophane filters, where students shone flashlights through them and viewed colored objects, reinforcing that white light is made up of multiple colors and filters selectively transmit certain ones. This is directly linked to the understanding of how filters are used in scientific imaging. Later on day 3, a flashlight experiment provided a direct investigation into apparent brightness. Students used two identical flashlights in a darkened space, observing how brightness diminishes with increasing distance. This served as a scalable model, directly mirroring why the sun appears brighter than distant stars, clearly differentiating between apparent and actual brightness. Day 4 transitioned to formal explanations, where students connected their hands-on models and scientific concepts. They reviewed the flashlight demonstration explicitly, linking it to apparent and actual brightness using provided text. These texts also formally define the visible spectrum as part of a broader electromagnetic spectrum and explain the mechanisms of colored filters building on their prior activities. Finally, the unit culminated on a day 5 with an elaborate phase, where students applied their understanding of filters and electromagnetic spectrum to composite images of deep space celestial objects from organizations like NASA. They learned how different filters captured various types of light, creating rich multi-wavelength views of the universe, and explained this process in a summative assessment.
Demonstrating understanding. Our evaluation phase, spanning 2 to 3 days, focused on students demonstrating their comprehensive understanding through argumentative writing and presentations. We began by introducing the structure of an opinion piece or argumentative essay, emphasizing that scientists support their claims with evidence. Students learned about claims, reasons, evidence, and conclusions, and we modeled how to identify these components in an example text. We then transitioned into the planning stage, where students identified their core claim for the essay. The sun appears brighter than other stars because it is much closer to Earth, as example. They brainstormed reasons based on their flashlight experiment and light properties activities, and drew upon factual evidence from provided texts about celestial distances and the electromagnetic spectrum. Graphic organizers were used to map out their arguments, ensuring a clear roadmap for writing. The core writing phase involved students drafting their argumentative essays. They synthesized their scientific knowledge and ELA skills using their plans to construct a coherent argument. We encouraged the use of using linking words and emphasized supporting claims with specific evidence from both their hands-on observations and the provided readings. Teachers circulated, offering individualized feedback on content, organization, and the effective inclusion of scientific evidence. Following the drafting, students engaged in refinement and editing, providing and receiving constructive peer feedback on their essays. They also practiced self-revision, strengthening their scientific arguments and writing quality. Finally, the unit culminated with students presenting their arguments to the class. This served as a summative assessment, allowing them to practice public speaking and demonstrate their comprehensive understanding of how the sun's proximity dictates its apparent brightness, supported by robust scientific evidence and reasoning derived from their unit-long exploration of light and celestial phenomena.